to give some lectures here, which I do actually on purpose also to get myself into a topic which I'm, well, starting to learn a little bit, which I think is going to be very useful in studying questions about, well, understanding gravity and how it's sort of related to space-time, but also many other things that are present in our world, in particular also quantum fields. They are all somehow underlying is some quantum nature of it. And the proper language now seems at least some new angle appearing from the angle of operator algebras, which by the way is an old topic, but somehow it has given a new ingredient into some of the discussions that are taking place. I know many, well, people here, and I know that a lot of you are working also on things related to quantum field theory. Actually, the reason for writing that topic down is that I can basically divide my friends up in two types of groups: those working on quantum field theory and really loving it, and there's another group which I'll talk about later, which I call the relativists. They basically love general relativity, and they work a lot on that. But I think somehow the questions are in the middle, because quantum field theory has many features or many even realizations that exhibit different features. Like there's, I'm going to write down a class of field theories that I think are going from very well defined to maybe less well defined. Very well defined quantum field theories are topological field theories, because they basically are very well studied. Also, they are defined mathematically. They have usually a very small set of states. I mean, things like Chern-Simons theory and so on. Then there's a very nice class of theories which I also like a lot more. Conformal field theories, also very well defined. And then when you start making it more complicated, there's still an interesting class of integrable field theories. But then suddenly when you start including things like renormalization group flow and things like that, you end up with a class of renormalizable field theories. And finally, which I think is the most general class, and actually the one that really I think is motivated in nature, is effective field theory. So effective field theory is a theory which has a cutoff, and which I think about as something that very naturally explains even where field theory comes from in a Watsonian perspective. And my point of view is that field theories generally are of this type, the ones that we describe in nature. And it also explains why field theories are so powerful, because of the Watsonian perspective. But then when you start taking certain special cases, you can end up in these kind of theories. But still, it's not the final story. And the reason is that field theories, when you think about them quantum mechanically, some of them are very well defined, but here things get a little more difficult because of all kinds of infinities that we have to deal with. So let me now write down what I kind of think about general relativity.
Sorry, quick question. Effective field theories, I think that you assume that they are not part of renormalization of field theories, they are non-renormalized.
So effective field theory is, for me, the point of view that you assume that there's always a cutoff, that you can indeed write down Lagrangians, the way you can separate the relevant and the irrelevant perturbations, but you can also allow certain irrelevant operators to be switched on as long as you stay below the cutoff. So effective field theory allows you to also classify perturbations away from your normalizable field theory. So the reason why I call this really how I think about nature is I don't think that field theories really should exist in the UV. I think that field theory in the UV has too many degrees of freedom generally. And the only way we use quantum field theory is always in a description of some physics phenomena at a certain energy scale, where we can always assume there's some energy scale larger where it's being replaced by something else.
The GR would be part of VFT in that sense.
That's correct. So I do think that the problem of quantum gravity is not the fact that we cannot quantize it. we all can always quantize it as an effective field theory. And I don't think that, and that is often a misunderstanding of what quantum gravity is that we don't have a theory of quantum gravity. We do have one, which is just the effective field theory. Except for the fact that it's non-renormalizable, tells you that in a certain way, when you start going to higher and higher energy, you have to fine-tune many couplings, which makes it not very predictable as a quantum field theory. But I don't think but general relativity also has other features, which I'm going to mention now. First of all, let me also make it clear that there's also a class of theories here which are better defined and worse, depending on what kind of space-times you can be working with. So there are 2D and 3D models of gravity that are very solvable, like indeed sort of the Chern-Simons formulation, or currently people are working a lot of what's called JT gravity, which is kind of an analog, say, of a BF theory and topological theories. But then when the space-time get higher dimensional, you can also distinguish them on their asymptotic properties. Many people now are studying ADS, and there's one reason why that's better under control. Usually also this arises quite naturally in supersymmetric theories. It's also a theory where asymptotic boundary conditions are easily defined. We also understand, maybe I should even include in here, let me actually do that. Because we of course have thought about these backgrounds also in the context of string theory. And string theory is a bigger theory than GR. But let me first think about perturbative string theory, which is also usually defined on certain backgrounds. And then ADS backgrounds and Minkowski backgrounds are quite well understood. But one of the bigger questions is how you go to cosmology, and then you have to go to the sitter. And really the more complicated one that we have very little to say about within string theory, for instance, are cosmological space-time. And I even think that as theories of general relativity, these models that we are currently using, well, I actually am very motivated in trying to understand better what's going on there, because I don't fully understand it from say, quantum gravity perspective. But the reason why I make this distinction is that, as I said, I have two types of friends: those that believe a lot in quantum field theory, and the other ones that feel themselves are general relativists that actually think that, well, Einstein's theory is kind of the most fundamental description of gravity that we can ever give. But I think there's truth on both sides, but there's also things that are not fully well, complete. And I really think that both sides need to be completed in some way. So this, of course, why we've been thinking about string theory. String theory, and then I mean the full non-perturbative string theory. Because one of the things we learned here is to connect general relativity to quantum field theory, and certainly ADS-CFT has been a very important well, theme of research. String theory also made possible to study black holes, and I'll come to black holes in a minute, because maybe I also have to tell the story that I grew up I did my PhD in Utrecht, where there was Erik Verlinde, who at the time that string theory came about, he sort of was criticizing it because it didn't address all the questions that we have about quantum gravity, in particular questions about black holes. That changed because we learned, well, there are things like deep brains, which are part of the non-perturbative definition, and that allowed us to well, make contact with, well, properties of black holes and so on. But if you now still ask, do people really understand what string theory is? It has many, many elements in it. But I think most people still like to put a question, and actually currently, well, first of all, this was a question that Joe Polczynski asked about a year before he made the discovery of deep brains. And I think he made a very important step forward. But currently there is also a program going on in the KITP with the same title, What is String Theory? Because I do feel that we have many ingredients, but we still have not understood what is going on there. So the story I was saying about holes was actually, well, I think eventually also important in making progress in making these connections. And so black hole physics I think the reason why I'm interested in it is not so much that I think that there we can have immediately evidence or do measurements of some observations, but I think it's a playground where we can study the questions of how to connect these different fields in a very, well, precise way, but also because there's a challenge there, which has to do with, well, properties of Hawking radiation and so on. And one of the things that we learned in recent years is that well, black holes have horizons, and that horizons are very special places, and that you should be able to ask questions about space-time in the neighborhood of horizons. And it turns out that the properties actually in a certain way, DR, for instance, knows quite a bit about microscopic properties of the theory that quantum field theories do not know. So one of the pictures I like to draw a lot, and it's always this picture where I think about the horizon as something that splits the space-time into two parts. And so this we can study in quantum field theory, where you also can ask questions about space-times that are like this, like if you have Rindler space, for instance. But the special thing that we know about from the gravity side is that there's something, a special thing about horizons. It's related to their entropy. And those discussions eventually led also to insights coming from what I call quantum information theory. Namely, there's something, a property that we can define, which is the entanglement entropy between the left and the right part of the theory, where in GR we somehow now have an answer which is obtained from a path integral picture. But if you ask me, do we understand microscopically what's going on? Entanglement generally counts, well, how states, quantum states can be defined on the left and the right, and how they are sort of connected in a state. Normally you would write down entangled states as sums of products of states on the left and the right, but precisely in quantum field theory we cannot do this. Anyway, general relativity makes a prediction that it's the area of the horizon over 4G, plus maybe a contribution that if there are quantum fields here in the log, there can also be an entanglement. So this is an entanglement entropy. Which now can kind of split into two contributions. One that is sort of has a gravitational origin, and the other one that comes from the quantum field theory. So this combination actually has a very nice property, and it's something that in recent years has become sort of emphasized a lot, is that quantum field theory, as I mentioned, has all kinds of divergences. And if you would calculate its entanglement entropy, there would be a divergence that would be growing like the area of its, well, of the surface that is splitting the quantum field theory into parts. So if we write down the state, say the vacuum state, and want to sort of define the entanglement of the vacuum, what I said, you have to sort of split it into a Hilbert space on the left and the right. But then the entanglement entropy generally diverges, but the divergence can then be absorbed in renormalization of Newton's constant. So in a way, Newton's constant then becomes a constant to absorb certain infinities again in quantum field theory. But the fact that this number is finite, it tells us something about the microscopic theory. Now, this whole discussion now is going to get a new perspective when we're going to think about these questions from the point of view of operator algebras. So the topic I'm going to describe is something that appeared in recent literature, and in particular Ed Witten in a series of papers has been sort of emphasizing that a lot of the discussion that is taking place in the black hole complex, and even in well, thinking about gravity and its relation to quantum field theory, needs a precise language. And one of the things that he knows quite well, and actually it's something that he worried about even in conformal field theories and so on, is that you cannot simply talk about splitting a state like the vacuum as say a sum over states that live on the left and on the right. And this has to do with the kind of well, operator algebras that correspond to quantum field theory. So if we think about a CFT, generally a CFT has a very nice Hilbert space. If I think about it sort of as living on a cylinder, if it's 2 plus 1 dimensional, or if it's higher dimensional, the cylinder, this can be a sphere of some dimension. It has a nice Hilbert space that indeed has well, good properties in the sense that we can talk about states, we can project on states and things like this. But as soon as you sort of try to split the space into 2 parts, like sort of, well, doing like here, by, well, cutting it in 2 parts like that, you also have sort of light cones sort of locally here. Well, I can draw this very well. This is one, and that's the other. Oh, let me do this better. So if I think about the cylinder, where we have 1 time slice where we split the space into 2, you can draw a light cone through this point. So this light cone sort of is being split here. Actually, you have a divergent entanglement entropy, and actually you cannot really write down tensor product of states on the left and on the right. The reason why Ed actually worried about this at Witten is that when he defined things like string field theory, he was actually trying to imagine indeed cutting strings in half, and he had a problem trying to do this. So the operator algebras that are associated to these problems, the ones I'm going to be thinking about, are actually the von Neumann algebras. And they are known to sort of range, well, from simple to much more complicated. So the classification that von Neumann already knew about a long time ago was that von Neumann algebras are operator algebras that kind of split into various types. There's something called type 1, which is basically the one that we know from quantum field theory, from quantum mechanics, and indeed quantum field theory is like conformal field theory. When we can think about its Hilbert space and even topological theories, they generally have very good quantum descriptions where we can think about Hilbert spaces and Hilbert states. So I think about this as sort of ordinary quantum mechanics that we learn about in textbooks. The other example, which is kind of well known, is type 3. And actually this is what we encounter when we deal with quantum field theories. Now, in the recent set of papers that Ed Witten wrote together with Jeff Pennington and John Dasarica, they actually noted that there is an algebra in between that is kind of relevant for the discussion of understanding formulas of this sort. Namely, they're so-called type 2 algebras. And it turns out that each of these types well, can even be divided up in smaller or can be classified even in more precise ways. But the new insight is that when you combine gravity in some clever way actually with well, a quantum field theory and include the gravitational effect, the operator algebra becomes a better defined one actually, because in a certain way this is the best one that we have. Turns out that in this case you can talk indeed about individual states. So the intuition I have is that in this case we have a Hilbert space that may be characterized by some energies, and then we can resolve individual state and you can project onto individual states things like this. So that's what we know about in quantum mechanics. In type 2, there we have still a possibility of talking about energy levels, but we're not able to resolve individual states. But what we can still do is talk about a finite density of states. So we have something like a number of states that we can talk about. Here,
is it important whether it's a discrete spectrum or continuous spectrum, even in quantum mechanics? Or the way you just wrote the type 2 one looks like they are usually having continuous spectrum.
so in type 2, one thing that cannot be done is project onto individual states. So if you would have a discrete spectrum of an operator, generally when its eigenvalues are discrete, you would expect to have an operator that projects on that. That's not possible in type 2.
But even in quantum mechanics, it's scattering states with it anyway.
That is true, but well, anyway, you're right that maybe in quantum mechanics we can encounter possibilities of not having the. So I will actually give the definitions later, but you will maybe in quantum mechanics you can make examples that would fall in this other class. But certainly many models that we know about in quantum mechanics kind of look like this. It's kind of the. Now I will actually now start sort of the lectures. Actually, I'm going to think about the math. This was kind of a motivation coming from the physics. I'm going to now tell you about what are the mathematical definitions, and then I will get back to the physics later on.
And somehow this distinction in the energy spectrum is the map to some distinction in space, so will allow you to, instead of separating the spectrum and the states, you can separate the space-time into.
Yeah, so okay, so one thing that actually is special in phenomenon algebras is that it's not assumed that I'm gonna be looking at an algebra that acts on the entire space. In particular, I think about the phenomenon algebra precisely as something that acts on the parts of the space, part of the space. And the reason why quantum field theory ends up in this sort of category is that if I think about quantum fields, I learned this kind of from the book of Weinberg, who emphasizes this, that you end up always with quantum field theory if you impose things like unitarity, locality, and causality, things like that, because then you know that operators on the left and the right, they have to commute, and you have a very sharply defined light cone. The other thing you can do is boost. So that means that the spectrum of states can be arbitrarily sort of boosted down and up. And somehow the locality of space-time forces you to actually not be able to factorize the Hilbert space, for instance, in the left and right. So the thing that I'm talking about here has to do with the properties of the Hilbert space that I would associate only with the right algebra. So if there would be a sort of a type 1 description for the vacuum, for instance, you would expect there to be a equation of this sort. Well, this can be, for instance, if I write down the Unruh state, this is a state that many people now like to write down, and it's called the thermal field double. Maybe I write it like this. So if I have a Hamiltonian here, which is kind of the one for an accelerated observer who can only see the right-hand side, that Hamiltonian would measure these energy states. Then the generator here would go down actually, but anyway, so it's a boost generator. But if you ask the observer to sort of to think about the Hilbert space, you might think there's a Hilbert space here that's labeled by its eigenvalues, and you can write down this expansion. This turns out to be a formula that is not sensible in the type 3 case, but this factorization is kind of an assumption that, well, doesn't hold in general. And so we're not going to assume that this is generally true, but this is not true for type 3. So the question I'm interested in actually is, so in coupling the theory to gravity, somehow we can make a better defined operator algebra. And one of the things that you hope comes out of this is that we learn something about the questions related to black holes, in particular, well, things like the information paradox. I will save those questions for later. I first want to now sort of go through definitions of these operator algebras, and then we'll see how to apply them in a context where we go back to the physics.
Tell us whether, let's say, quantum mechanics is a representation of this algebra, or algebra just adds on the Hilbert space of quantum mechanics. Same about QFT. The role of the algebra. Basically, you give me algebra, do I know the theory, or I have to consider representation of this algebra, and that's my particular theory?
So one thing that kind of helps in thinking about this is that we try to add structure as slowly as possible. So we're going to start very abstractly. And one of the things that I noticed that the mathematicians do is that every algebra, which is unitary kind of related, they think about them as the same. So we're not going to be asking questions like, what do these operators really mean? And so in quantum field theory, generally, when we write down Lagrangian and we have fields, we have a very precise idea of what these operators mean, and we have a physical setting in which we're doing it. Here you kind of are working, well, I would say almost bottom up in the sense, one of the nice things about the theory that I'm going to be explaining is that many of the properties of this space-time actually can be derived without knowing anything about what these operators really, what their origin is. So we're going to sort of go, so this is why I think the language of operator algebras is very well suited to start thinking about where these structures come from, because I do generally think that this is all kind of an emergent kind of picture where microscopically the world is quantum mechanical, but then, well, the way that we then finally get into the quantum field theory is by taking particular limits and maybe certain representations of those operator algebras. But
so this is true that the type 1, type 2, and type 3 are basically it's all of them are the same. What type one, all type ones you can give me, they're isomorphic to each other. And
Because we know that every Hilbert space kind of
Right.
finite dimension countable one is the same, and that these operator algebras act like matrices. So the classification of this one is very easy. It's basically the dimension of the Hilbert space. And of course, you can still talk about well, what kind of operators do we allow and things like bounded operators. But as operator algebras, they're kind of all equivalent. But I'm gonna make actually I think eventually where we want to get answers to questions of how do we combine gravity and quantum field theory, I claim kind of the following is true. Quantum field theory fits in the type 3 category. When we add gravity now, actually in some limit, by the way, it's a limit where G Newton goes to 0. So there's not really gravity, but there's some observables that you can add that bring you in type 2. But if you want to have a meaningful answer of interpretation of this term, you better be able to count the number of states that are being entangled. You actually are forced to end up in type 1.
why don't take product of type 1 and type 2?
You can, but I think I believe that indeed the world is quantum mechanical, but in a way where we can do quantum mechanics in the world, as we learned in textbooks. And although we may have continuous vector, which by the way usually has to do with non-compact spaces, but I think when we describe the world in type 1 and try to emulate kind of quantum field theories, gravity is a consequence. You cannot do it without gravity. This is kind of going back to the paper I wrote many years ago about the origin of gravity. I think when you start understanding this entanglement and you start moving things around, actually the finite, if the entanglement entropy is finite, which is true in type 1, G Newton is finite, and you should get gravity out of it. So I like to understand this arrow of how to build the space-time out of these algebras. But it appears that the arrow of kind of emergence goes this way, because these algebras will be limits of these ones. So that's also the way that von Neumann thought about this. He thought about it as a mathematician. He wanted to think about operators that, well, where we can define a topology, like a topological space. So one of the things that defines a von Neumann algebra is that, well, what is a von Neumann algebra? It's basically an algebra that is closed. So let's M usually is the letter we use for a von Neumann algebra. We think about operators in the von Neumann algebra. If we multiply two of them, of course, we can be in the algebra. There's a property which is like emission conjugation or star operation. But the thing that he wanted to add to it is kind of a topology. And so when we think about, well, this algebra indeed can act on states. And one of the things you can ask is, well, let's think about matrix elements. So if psi is a state, I can think about matrix elements of this sort. And then if I have a sequence of matrix elements that when I take n to infinity approaches some limit, then that operator should also be in this theory. So if I think about this as just C numbers, and I define operators in such a way that this is equal to the limit of the operators. So this is then say some closure that I define of the algebra, which is called closed in a weak topology. Anyway, that is a von Neumann algebra.
And the psi and eta, these are states when you said the assume.
Sorry, I wrote them out the other way around, so it's fading, right? Of course. So I assume them.
Just remind, I personally read it when I was a student. So when he defined it, did he assume that states are states in some Hilbert space or in some whatever Hausdorff space or some? Is there a precise definition where this algebra acts? Or did not specify. Because this kind of reminds more like putting a separate Hilbert space and you have a limiting procedure. But is Hilbert space assumed or not? During any dimension.
Well, it is assumed because there is an inner product.
Well, there can be what's called Q-symmetric, that can be just Q-symmetric product in some space, doesn't have to be Hilbert.
I suppose it's the standard one.
Do
The
you have
question
norm?
is whether this Hilbert space is separable or not.
I mean, is there do we put some L2 structures, square integrable states in somewhere or?
Well, I'm gonna give a different characterization of von Neumann algebra, which is kind of this famous theorem that was proven, which doesn't allow use any states to begin with. But somehow I have to admit that I don't know the precise. Let me actually. There is.
So the reason I'm asking is the normalizability are states are this whatever objects normalized. There is a notion of norm which is finite that we can talk about normalizing on delta functions and densities or the numbers.
So what I think
differences are like in quantum mechanics, it's numbers, and in quantum fields, it's densities. Is this related?
so. Actually, what I think I assumed here indeed is that I'm working to write this thing down. I'm working in the class of bounded operators on a Hilbert space, but the definitions I'm going to be giving are going to be. I'm going to change this to a new definition that's going to be more general, where even the assumption of this Hilbert space might be sort of relaxed. Because it turns out for the case that the algebra that I was talking about the bounded operators on a Hilbert space, or let's if H is an Hilbert space, this would be the space of bounded operators on that, and that is a von Neumann algebra. But I can also think about limits of this sort when it's closed under these kind of limits.
But is it a separable Hilbert space or non-separable in general? In quantum mechanics, we usually impose the condition that Hilbert space is separable.
Well, this is where I show my ignorance in the sense that I don't know. So I don't know what is. So let me. I call this an example at least of a von Neumann algebra where this definition is going to be actually equivalent to another definition that I will give you now another definition that does not require the Hilbert space to be there.
You see, in old days, in 60s, I remember they proved that if you are 1 + 1 dimensional quantum field theory, there is still a chance to have the bounded operators in Hebrew. But once you go higher, let's say 3 + 1.
Yes.
People even made the claims that there is no such thing. You cannot consider the rotation in Hilbert space when the diagonals are what's called Fredholm operator.
Yes, okay.
Hilbert Schmidt doesn't exist. It's only in 1 + 1 dimension. That's what they say is the difference between 1 + 1 dimension and 3 + 1 dimension. This should show up somewhere in this classification because 1 +, let's say CFT. CFT looks more like, to me, more like type 1. Like
that's right.
Mechanics, right.
So
and I know the reason why, because all these properties are.
So when you look at the Hilbert space on the entire space of the cylinder, then CFT is a type 1 algebra.
But QFT is not, and CFT is part of QFT.
No, sorry. What I say something, I mustn't be, well, anyway, I'll make it more precise. The thing that's not the type 1 is when you ask the algebra associated to a finite part of the, so if you want to define the sub-algebra of the, so even for CFTs, if you want to define the sub-algebra that acts only on part of the space, that's not a type 1.
That was Witten's problem in splitting.
That's right, that's exactly this problem. So the problem is that when you cannot define the operator, so this locality question about if I want to define only the algebra on the left and ask whether that algebra is represented on a Hilbert space, well, it's the entire Hilbert space, but it's not like there's a factor involved here. So I'm going to define factors in a minute, because the thing that I'm
Yeah, yes, I completely agree. So the problem, sorry, I'm engaged in discussion, but the problem was that in general, in CFT, you don't have to speak about space and time. You have the dimension of operators, you have whatever.
well, there is radial quantization, things like
Yeah.
that.
So the problem starts when we think about the space in geometrically, that when we have
Yeah.
line, now we have to split. But if we define CFT like in BPC,
That's correct.
what is
So
the problem?
no, but that's also more. I agree, but okay. So I do think that the full Hilbert space, I mean, the full algebra, you can separate it out. Is fully type 1.
Okay.
And so, for instance, when people write down this also for the thermal field double of CFTs, this would be a good way of writing it, because the two CFTs are actually type 1, and you can write this thing.
So isn't really the question how to understand everything that we understand in quantum information language in some other language? That would be more reasonable to use in CFT, for example.
So the thing that I hope will come out of this is that in making this step to go to these kind of algebras, that we have better tools to answer questions about sort of the black hole information paradox, but also what more microscopically goes on. Because one of the ways we actually think about black holes is actually systems of this sort, which are sort of chaotic, which have a density of states and so on. The other thing that namely is possible in type 2 and not in type 3 is that you can ask about smaller Hilbert space, where you can actually define the difference between the dimensions of the two Hilbert spaces. This is actually what actually will be not possible in the type 3 case. So, and actually the problem of the black hole information paradox has actually to do with this requirement that quantum field theory has this very strong locality requirement that operators outside of light counts cannot, they always commute. And so it seems almost impossible to send signals from one to the other, but this is kind of where type 2 algebras will start doing something else. I think eventually this will merge with things we know about string theory and maybe other, or ADS CFT, because I will put it in that context.
So there will be a limit in which you can go from one to the other.
That's correct. Actually, there's very important relationships between these two algebras.
Seems to me that the one really possible help from this might be that you will know that if you are, let's say, type 2 setup, that certain questions are not allowed to ask, because these are not properties of type 2.
That's correct, but at least you can ask more questions than in type 3. So in a certain way, this is the least well-defined one.
Right, but this locality you mentioned, like in string theory, we always have a problem what we mean by locality, because you have infinitely many string field, which is expanded into infinitely many fields, tachyon, vector, and so on. You don't know what locality means anymore, because at infinite sum.
No, but maybe I should indeed already tell you now this other definition, which is kind of, I think, related to the question of locality. So if this is a phenomenon algebra, there might be operators in the same theory that are not part of this, namely, there are also operators, so all the operators, so I call the commutant, namely, there's also another algebra, which is the one that commutes with all these operators. So this is the set of all these, so that B and A is 0 for all A and
M prime is a subspace of algebra of M.
no, it's commutant. It's a separate one. And that's exactly how I think about it, because M is the operators here and N prime are the operators here. So I kind of have already now defined for you some notion of locality, or maybe I should call this B prime. So these are operators that are not the same as those. There may be elements that are involved, but we will generally look at cases when those elements are just the identity.
In that sense, you can define through locality what space like interval means. If the guys commute,
So I think this part of the phenomenon algebra starts making things like space kind of already there, because you can say whether something is on the left or on the right. You're kind of putting a separation between the left and the right part of your space. So then there's this theorem by von Neumann and Murray that tells that this definition kind of is this equivalent. Well, let me actually write it down. You can also consider the commutant of the commutant. And of course, well, you can see quite easily that every element of M is part of it. But if you complete it by also including all those limit points, then that's all. So the same equivalent definition of von Neumann algebras is that those are algebras where the commutant of the commutant is equal to M. And in this picture, it's kind of sort of clear. You go from this to there and you go back again. But this picture actually, I know describes accurately what's happening in type 3 algebras. And I'll say more about this, because actually from this construction, if we are in type 3, we can indeed generate a lot that already looks like this picture.
but those properties are generic for all type 1, type 2, type 3,
That's
or,
correct.
or specific to one of them.
No, this is generic. The way to distinguish them has to do with looking at certain projections that are in this. I won't, well, I have the proof here, but I won't go
Do
through
you
it.
want to make a break in?
So one of the important notions in algebras of von Neumann algebras is called a factor. So a factor means that its center of its the elements which commute all the is basically just the identity. So that means also when you look at Hilbert spaces that are finite dimensional, that would mean that there's a set of operators that acts on a factor in your Hilbert space. So you can really think about sort of having an extra part of your Hilbert space that you factor in. Now, the thing that defines these different type 1 and type 2 is properties of projectors. So maybe I should first, before I study projectors, talk about a representation of these these algebras, which is called the GNS representation. So when I have a state on the algebra, that's actually defined as a map of the algebra to the numbers. Maybe actually should even take the real numbers, because then I can define. So this you can think about as well, either taking the matrix element of these operators, but you can also think about, since I can think about the algebra as acting on only part of the space, this could also be a density matrix. So it takes the operator and then takes its expectation value in that density matrix. Yeah, actually, maybe I'll take C, because the norm that I'm going to define now is taking this defines now an inner product that I'm going to write like this. This is a formal notation, so I'm going to introduce a representation on. Sorry, the star is here. So anyway, this is already an inner product of the state with itself. Because now I can think about a representation of the algebra by acting on the algebra from the left. Now, this is a inner product if I assume indeed that there are no elements where this is zero.
In this notation, phi of A would be bra A. Just can you write phi of A?
Phi of A, so I have I'm using actually a map of this sort. So where this is a positive real number to define an inner product. So maybe I can even do it more generally like this. So the inner product is really defined like that.
And the identity operator responds to what? I guess that's the question, right?
So the identity operator then is sort of a unique state, sort of a state on which you build your GNS Hilbert space.
So you have an algebra and you consider the representation of this algebra basically where operators act on the algebra itself, right? So you identify the algebra as
Basically with its left multiplication.
right.
So this is kind of like in groups, this is what you call the regular representation.
Yeah, so this it has space of functions on M, complex functions, C, and the algebra acts on the left.
Yes. There's also an algebra that acts, a representation of the algebra that acts on the right, and that will play an important role later, because in a certain way, when I think about these two algebras that commute with each other, there's also an action. Well, that goes like this. You take the star of, well, let me call this, there's another action that acts like that. That's also a representation. And actually this one commutes with this one. So one way to think about the two commuting algebras is actually in this form of the GNS representation. I'll come back to this later because it actually is important for various type of algebras, particularly type 2 algebras. But I think I want to quickly get now to the definition of what are these two different types.
Sorry, this is probably my ignorance, but is a polynomial algebra always a C-star algebra?
Yes. It has some extra structure, which is this weak closed under the weak topology. You want to quickly scan if I forget something about the GNS representation here, because I think
What are the properties of this inner product? Of this function phi?
well, basically, it's the properties indeed that there must be a map that does this, and also indeed has the property that this is always larger or equal than 0. Then this defines the representation. The point is that you may ask is whether this labeling is unique, and so there are things that are like there could be states where this is equal to 0, or algebra elements where this is equal to 0. Then you have to divide that out in this this representation, because they would lead to the same state in your Hilbert space.
What about triangle identity?
Actually, I think it must be satisfied. Yes, because I mean this is called
So it's a metric space, is it?
it's a let me see what the official name of this thing is. It's a linear functional, so it's linear. So this linear properties probably would be sufficient to prove the triangle inequality in this case.
Since type 1 is quantum mechanics, everything we know about quantum mechanics, we just can rewrite for type 1.
Well, no, but anyway, this is gonna be true also for the other.
Right.
Sorry, I haven't seen this in a while, but like, isn't the statement somehow there exists a representation of the von Neumann algebra? So isn't it given a state, there exists a representation which represents that state?
So when you have a state, then you have naturally a representation associated to that.
Yeah.
And so the states you can have, I mean, of course, you have many states, and then this inner product and the representation will depend on that. When I talk about type 1 and type 2, actually for type 2, there's actually a special state that you can define, because in that case, you can define a trace. And then actually this representation is actually the only representation basically that you need to know for these type 2 algebras. So what I want to now get to is indeed the definition, which has to do with projectors, and a projector is denoted by P. So it is a, well, you can think about it, it must project on a sub part of your Hilbert space, but they can be ordered in the sense that intuitively you can think about projections on, well, part of the Hilbert space, but then there can be a projector that even projects out more. So there's a natural ordering of projectors. So if P and Q are projectors, we want to sort of define what this means. It turns out that in that case, there must be an element in your algebra such that P actually can be written as, and I put a star here. So this is a positive operator, and actually this is also what a projector should be. So there must be a U that does this. And then I can construct also the operator where I put the star on the other side. And the property that I must have is that this is actually a projector on a subspace that's smaller than that of Q. So that means that this is equal to that. So if these two properties hold, then I say that P is smaller than Q. So that means that P would project on a smaller Hilbert space. Oh yeah, you might say a smaller set of states in the Hilbert space. So for finite dimensional or for ordinary quantum mechanics, these definitions are very clear, but you can make this now true for any von Neumann algebra. There's also a notion when two projectors are of the same size, at least they're equivalent, basically that you have an inequality of this sort and the other way around. And that implies that basically Q itself must be equal to U star U. So we have this relation and that relation. Because then this projector basically is projecting on the same Hilbert space, well, the same size. So now the definitions of the von Neumann algebra have to do with two special things you can say about projectors. A projector is finite if the following is true. So if P is smaller or equal than Q, and we also have this second property, so that this is also true. Then P must be equal to Q. There's another property which is called minimal. And basically that there is a minimal projection P Well, let me actually call it,
Why p squared is equal to p?
sorry?
Well, if p is a projector, then p squared should be equal to p, right?
So given that it's a projector, there could be, so this is not clear from this way of writing it. But given the projector, there must be a U that allows you to write it in this way.
So what Sergey is asking, let's square it. I get u star times u star.
Yes.
Only I see that it's u times q times u. Right, that's only identity I see. I
So-
don't see why it's p again. It should be simple, actually. Just, u star. Oh, it would require completeness in some sense. Normally, we would say that u star squares to u star, because u star u is one.
That's right.
But u star u here is not one, it is q.
But it's one on the space that you is
Acting on
you is acting on anyway.
Q acting on u is u.
So I think this relation will probably hold.
If that holds, then we are done.
Because basically this is projector on the space that you act on.
Yeah.
So basically this operation takes the space on which U is projecting to the space that Q is projecting on.
Okay, q acts that way. Yeah, because q acting that way would give me u. So let's act by q on u that way. I get u.
Yes,
And then p acts this way on u, and I get again u.
yes,
So q is projector when I act on the left, and p when I act on the right.
yes. Okay.
And then both square to themselves. So
That's indeed true.
So we're basically using that u star u kind of acts as identity.
As the identity on the space on which P is acting anyway, and that is kind of what you're using if you need. So there's also a minimal projector, which means that anything that's smaller than this one must be zero. So if it's not equal, so if I have some projector that obeys this, so maybe, yeah. So that means actually there's something like a projection on a single state. You cannot project on less than a single state.
Is that a definition or the claim that such a thing exists?
It's a definition. So these are definitions. So finite means this property, and minimal that means that if there is a Q, say that's smaller than P, but it's not equal to P. Then Q must be zero. So then the definitions of the algebras are as follows. Actually, type 1, all projectors are finite, and there is a minimal projector.
Definition of minimum, what's the condition on p?
So if this is the minimal one, let's say this one,
Okay.
then this is what must have. Well, actually, this one may be even sufficient for type 1, because actually,
Confused with q equals 0. Because q, as we agreed, acting on u, gives me u on the left. So now, how is it possible to have? Q
so that's only when they're equal. I said this relations.
Right. So can Q be zero? Because if I apply Q equals zero exists, then this is violent. Oh, something else, probably.
No, I,
Well, actually,
Zero,
P
zero.
is less than Q, right? So in that formula, Q cannot be equal to zero unless P is zero. And in that formula, Q is less than P, so Q can be equal to zero.
Well, there's another problem, yeah.
So it's fine. Yeah.
It's okay. Let's,
Well, I'm saying that I have this definition.
Yeah, but there P is less than Q.
But P is less than Q in their P.
No,
Q is less
there
than P.
Q is less than.
Oh, sorry, I missed a lot. Okay, Q is less than P, and then this doesn't apply, this definition doesn't apply.
Sorry, can I kind of try to summarize whether I understood the definition?
yes,
So you consider an arbitrary algebra, yes? Then on this algebra, you have this function phi, basically a scalar product, right?
yes,
And then you have projectors satisfying these properties.
I think actually those relationships here are not even requiring this representation.
So it's not necessary, right? So
That this representation might be there, but this is something that I can define without talking about the states or the
so
phi.
for Neumann algebra of type 1, it is an algebra which has projectors satisfying these two conditions, and that's it, right?
Well, yeah, actually, I noticed this one actually that distinguishes type 1 from the other one. That there's a minimal one. So type 1 indeed has sort of possible that you indeed can project on single states. Which, by the way, is also true if you have a continuous vector, by the way. Anyway, it's the idea that you can project onto single states. So type 2 actually splits into two kinds. There's type 2.1, which also has this property, is all projectors are finite, but this one doesn't hold. So there's no minimal projector, but it's true that every projector is finite. That means that if it's smaller, but also, well, anyway, that this is implies this relation. So actually, by the way, the projector that's called finite, by the way, is Q. So if Q is finite, that means that any projector that is smaller but also has this relation must be Q. And that is actually the property that holds also in type 2.1. If, by the way, if it does not hold, it's called infinite. This property sort of is violated. So type 2 also has a class that's called type 2 infinity, which has finite and infinite projectors. Because actually what I should have said over here also, I think this holds in general when the Hilbert space is finite. If the Hilbert space is infinite, this thing may not even be true for type 1, but this is always possible. But type 3, and this is really where everything is not. Well, type 3 also has various classes, but the one that I'm going to not mention too many of them, but type 3 in particular has no finite projections and also no minimum. So that is what leads to the classification. And these two are the ones that I indeed will be also talking about more. And actually, they will have relationships also with the type 3. And this is where indeed the new kind of, I think, developments are happening, is trying to understand these type of algebras in the context of, well, basically quantum field theory coupled to some form of gravity.
So I'm just trying to figure out, how is it true that in all quantum mechanical systems, all projectors are fine?
No, I think this is true if the Hilbert space, of course, is finite dimensional. So this
But
is
the
not.
spectrum is infinite.
No, actually, this is indeed not one that's not necessarily true. Actually, I think you can have also infinite ones.
Okay, then what I have to understand is basically that in all quantum mechanical systems, even that spectrum is infinite.
Infinite, there is still
There is a
a
minimum.
minimum project. That's correct.
So that's a true statement, and we know that statement. That's trying to figure out.
Well, I can go even for the harmonic oscillator, which is basically one that's already type 1 infinity because it's an infinite Hilbert space. I can still project onto a single energy eigenspace. So
Is it equivalent to saying there's no band gap?
So the question is whether, I mean, the system I'm always confused about is even the particle on a real line, because it has many different things like, well, P and X are not operators that you can really define on the infinite line. But the infinite line has no gap because it says it's zero, almost zero ends. But I can still talk about projection on a certain momentum state or something like that. So I think that that's still is something that would be.
No, momentum state that does not belong to the space.
Yeah, that if you say square integrable.
But you can always have a normalizable state.
A normalizable state that you can project from. Yeah.
I think it's probably related to whether the Hilbert space is separable or not.
The other thing that is important for these algebras, in particular for this one, is that there's a notion of a trace. And in this case, even the trace of the identity can be defined. And then you can take the trace even in constructing this Hilbert space. Because, well, instead of writing phi here, I take the trace. And that actually defines a representation of the type 2-1, which is called the standard form. It's basically the statement that that's the only sort of meaningful representation of type 2-1 algebras.
Let's for a second try to understand why QFTs normally are type 3. So we have to explain that in QFT generically we cannot have finite and minimum.
When we are confined to a region of space, that's say only the right side of our line, sort of like that, then this is true, that you cannot have a minimal projection. And so there's this factorization issue about the state on the real line not being factorizable in the left and right.
That way,
It's exactly the same.
Ball, inside ball and outside. I go radial quantization, I take a ball,
So-
inside, outside.
so the
Can I
conform-
talk about inside, outside?
So the conformal field theory, when we put it on the cylinder, as I said, is type 1, in the sense we can define states and so on. It's but it's not a factor, because here I'm talking about indeed sort of subfactors of the full theory. Anyway, this is the classification where indeed we assume that this algebra is not.
I'm probably saying it the wrong way. I try to figure out 5/4 something I teach actually. Can I explain that? Let's say 5/4 theory is type 3. Can I explain that easily? 5/4 theory in 4 dimensions. Well, I construct the box space, right? Even free theory, actually, free color field, quite good. Why is type 3?
have operators. You have operator distributions, operator.
No, but I still can project. I mean, I can take one particle state, two particle state, I build the Fock space.
They are not normalizable, they do not belong to.
They are normalized by delta function. That's what the point I was saying.
No, that's, they are not included.
If it's normalized on delta function, it's not.
Well, you use a consider normalizable states or.
Or then
you
you have-
consider packets, yeah?
Then it's obvious in any quantum field theory where we teach that it's a delta function normalizable states from type 3.
Yeah, as soon as you have on those states, you get problem.
Right, but did you say quantum mechanics on the real line is type 1?
No, quantum mechanics.
Or sorry, that's a question.
That's one, yeah.
So it is.
Because it's a Hilbert space, you can introduce discrete basis in the Hilbert space. It doesn't matter whether it is free particle or non-free particle. There is no Hamiltonian here yet.
Yeah, but there's a momentum operator.
There is momentum operator, which is not bounded.
Then it's not like this.
Wait, sorry, in quantum mechanics, if I have continuous spectrum, I again have states normalized on delta functions.
Yeah.
So I should say that it's also type 3.
That's
You can have the states, but they will be normalizable, right? So physical state is normalizable in quantum mechanics. It has norm 1 usually.
You're saying that even if I have delta function normalizable states of momentum or something like in quantum mechanics, I am basically bounded to have really normalizable states,
Yes.
which are wave packets of that,
Yeah.
which you say I don't have in QFT.
Right. You don't have normalized.
Vacuum is supposed to be the state which is normalizable on 1.
Yeah, and you know very well that there is no vacuum in quantum field theory as a state is norm 1.
Actually, in supersymmetric ones, there is. Yeah, there is in supersymmetric ones a normalizable state, which is a zero energy state of Hamiltonian. And
There
it's
is no Hamiltonian there, right?
well, I mean, there is a notion of, I mean, really good vacuum state, which are some cases, let's say for n equals to 2 supersymmetric ones, which are discrete spectrum and they're normalizable. Like, so basically, oh yeah. So those supersymmetric theories, which have gap and that have the vacuum states described by topological quantum field theory, will not be type 3. Right? So we say that topological quantum field theory is a vacuum sector of gapped supersymmetric theory. And it's equivalent to quantum mechanics. So yeah, it's a good question. Listen, take the ones that we call topological quantum field theories, which are vacuum sector of supersymmetric theories.
Yes.
They will have perfectly normalizable vacuum states. They're THs, they're type 1.
Yes. So it's not like, but okay, type 3. I mean, I'm not saying every quantum field theory is type 3.
Oh, that's not true. That's okay. It's not true that every quantum field theory is
Type 3, but the point is that in when I talk about the space on which the field theory is defined and want to define the algebra that's only associated to part of it, that is a type 3 algebra. So it has to do with how we separate the space into 2 parts. So the type 3 algebra describes only the algebra as a part of the space. So the same for topological theories. The question is whether you can do something like this, because I don't think this is actually meaningful to do for topological theory. Actually, my feeling is that a topological theory has only operators which are basically in the center, in the commutator of the 2.
in commutant.
Yes, I mean the intersection of the 2, because I think it's kind of where you have states that live neither on the right or on the left. Because I think the localization of the state is not possible in that case. You don't localize states in topological theories because they're not.
So we have this abstract state, which is can be worked out sometimes. Let's see. The well-defined TQFT is equivalent to quantum mechanics. Remember, you have the chiral ring operators, they are mapped into commuting Hamiltonian.
That's right. So those are, as I said, actually in my list of the topological theories and also conformal field theories. When you look at their Hilbert space and the algebras that on them, they would be perfectly fine type one.
But if I decide to go to the massive space, I go from vacuum states, which is a topological quantum field theory, to excited states, then I suddenly become type 3. Somehow type 3 has to have type 1 as subalgebra.
Oh, these kind of things are possible, I think. Anyway, let's discuss examples
just
later.
created, right?
Yeah.
So suppose the full physical theory is type 3.
Yeah.
Then I claim that there is a vacuum sector, which is definitely type 1, because we just agreed.
Well, let's discuss this.
Yeah, okay.
I want to just do one final thing because it's running out of time a bit. Well, there were many things I want to discuss, but one thing I wanted to make a little more clear is how to think about this picture also in these algebras. I already mentioned this representation. So, and indeed, there's two representations where you multiply the algebra x from the left or an x with the conjugate from the right. And this is actually a representation of the opposite sort of. So the way it's written for type 2 usually is that I think about two algebras which are kind of isomorphic, namely the one that acts on the left and the one that acts on the right. And there's a map that takes you from one to the other. I can do the same actually for type 3, and actually maybe this is the case I want to spend the last minutes on, where I want to get this picture out of, well, thinking about the type 3 algebra in a similar way. So this would be indeed be then the commutant of the algebra. So here we would have m, and there we would have n. So what is special about type 3? Sorry about this. I'll write it for this case. So we're considering type 3. And when I think about the state, which when I'm thinking about this state as being the vacuum in this Hilbert space, it has two properties that are important, which are called cyclic and separating. So cyclic means that if I act with I take all the operators in M and I look at the span of this set of states, that this is actually the entire Hilbert space. So I can generate the entire Hilbert space by acting with the operators in my, say, on the left-hand side. So I don't need to do anything on the right-hand side, and this is just sufficient for getting all the states. Separating means, so this property. So also we find separating as that if an algebra element is 0 on the state, then it means that A is equal to 0. Now, I did not talk about yet this part of the space, but I will introduce it in a bit, because there's still also in this case something like a DNS representation that you can make, in the sense that I can identify, therefore, if I use this property, I can write these states basically again as the states associated to A. And similarly, as I wrote there, there's an action also of the same algebra from the right, which you can think about as the way of constructing the commutants on the other side. But the property I want to use now is that since we also have the star operation, this fact that I can generate the Hilbert space by acting with A's on the state, also I can do the same thing with acting with A star. Wait, I remember correctly now, let me think. Boy. So if I think about all the states constructed in this way, there is a map that I can apply here, which is called S, which gives me so I take all the states I get by acting with A star on the same state, and I consider all the states that I construct this way. Both of them generate the entire Hilbert space. So there must be an operator that takes us from the this set of states to this set of states.
So long as this operator is part of M.
It's not. It's not part of M. And because, I mean, both of them can be defined, but there's no operator that takes us that way. This is called the Tomita operator.
There is operator which does not take us outside of the space of states, but does not belong to M. So we have space of states, another way of writing same space of states, and we have operator.
An operator that relates
And that operator is outside.
Is outside of the so the star operation in a certain way is not part of an operation you can do within the algebra.
So this is property of type 3,
This is a property of type 3.
but not type 1, obviously.
So this operator does not exist for type 1.
There are things you can do similarly for type 1 and type 2, but this is, let's say this way, actually most of what you can do for type 3 you can also do for the other cases. Actually, I already mentioned for type 2 I can do something similar.
So for type 1, such operator will be 5. It's one of function on M, because I can construct this as coherent exponential, some invariants and blah, blah, blah. So for type 1, I think this S is one of 5s.
Well, actually, I'll tell you what it is for type 1, because you can actually work it out for type 1. Well, let me actually erase this. Because for type 1, you can think about this operation as, well, in that case, you can take a trace. So if I have an algebra that only acts on part of the space, then I can take the trace over the other part, because in that case, I do have a Hilbert space, and I can define a density matrix. And so, which I call rho. So the state, in that case, I have a state, and I can trace, say, over the right, and define my density matrix for the. It turns out that this operator in that case can be thought about as sort of a square root. So it actually acts on the left and the right. In this way, actually there's a density matrix I can define on the right, and there's a density matrix I can define on the left by also taking the trace. So this is the one on the right, and that's the one on the left.
Okay, and it's claimed that S is a bad function of M. It is a function of M on M, but it's some kind of bad function. Because it is, we just wrote it as a function on M, or some kind of weird function.
So here it's something that acts both it acts on both sides.
So first of all, rho is a function of on M. The way it's written, it's a function of M.
Yes.
My question is, probably trick is in tensor product. So I have two M's or I have n times m, and this is a function on n times m, and not on m.
N times M prime?
Now, maybe I should have made it more clear.
Because the way I think Eric is like this. So by defining the a times omega,
Yes,
we are one basis in the space.
yes,
A star omega is another basis in the space.
That's
so in
right.
the space, we have two bases.
that's correct.
Now, if this space is good quantum mechanical system in that space, there is an operator which takes me from one to another.
Yeah, but that operator may not be part of the algebra.
There's a part of algebra that does not satisfy one of the conditions. Like normally they would say that operator has a bad norm or something, some kind of, it's not
Well,
Hilbert Schmidt, whatever. It's
I
not
can
valid.
tell you, okay, maybe I should give the intuition that I have, which is namely the one that I know from basically the state I wrote down, that is the vacuum state when we have left and the right. So it's the state that, well, let me write it down as if there are particles which have energy omega, then the vacuum state can be written like this. So I have particles on the left and on the right. So this is the way that the vacuum state kind of would look if we would imagine that we have the left and the right Hilbert spaces. So when I add with A on the right, I might actually take away one of the particles or add a particle. There's also an action that acts on the left, which is the A dagger. So in a certain way, what you have done is you have shown that this state satisfies the following property, that if I act with A on the right, it's the same as A dagger on the left. But suppose I would also include in this map the exchange of the left and the right.
That's not a
That's correct, but that's the way that this operator is going to be defined. Actually, it does exchange the left and the right. So this is exactly what happens in this Tomita Takasaki theory, is that this operator basically allows you to take an operator that yeah, because yeah, maybe I should write first down the definition.
Maybe we can continue next week. It's almost 1 o'clock. What the people?
I'll just finish with one equation. Is that fine? So namely there is a decomposition of this operator, which is called the polar decomposition. And I think I wrote it. J is on the right and on the left. Yes. Another way of saying this is that this operator delta, which is called the modular operator, can also be written as S bigger S. And J is an operator that squares to 1. And basically, it is the operation that indeed exchanges the left and the right. So if I would think of this, actually, you can think about as the way I wrote it, actually, as an operator that
yes, it is very similar.
as the density matrix of the right and the left one. Well, this operator, I actually didn't write it down exactly as I should have, would have been this one. Something like that. It has an odd diagonal part. So I can think about J actually as an operator that has sort of this form, that it actually exchanges the left and the right. So this is why it squares to 1. So in terms of the algebras, what it does is actually it maps the algebra, an element in M. Then you can write down J, A, J, which would then be in M prime. So you basically have a map from the algebra to its commutant. And in pictures, I think about this as that I go from the left to the right. Except that you have to make, actually it's an anti-linear operator, anti-unitary operator. In the sense that it actually, when you multiply it with a complex number, actually there would be complex conjugates on the right hand side. I will actually use this later to basically construct what is called the modular flow, which is this operator actually in a certain way will act as a generator of a flow on the algebra, which in terms of pictures indeed is the flow that would be associated with the Hamiltonian that goes here. So I didn't use a lot actually of the algebra. I basically assumed that there is this operator because of the fact that the algebras can be mapped onto each other. But in terms of this operator, you can construct new operators, which are this modular conjugation and this modular operator. And then actually the next thing I will talk about next time is indeed sort of this modular flow that will describe, well, what sort of locally happens in the space-time.
There were many questions.
Well, may I ask just one
Yeah, go ahead.
question? So this, why A star already belongs to the left guy, right guy?
What do you mean? The left or the right guy?
Yeah, so A omega gives you something to say on the right, right?
That's correct.
Then S maps to the left.
That's correct. But then the same state can be represented by an A star on the right.
By A star on the right.
So I first map it to the left. So when I said here, this example, actually here we have an example where so what this actually means is that
There is no M prime here.
no, but this somehow secretly makes this S actually turns it into an operator that is actually in M prime. Then it acts on the state. And then that state that you obtained is the same state that I can act with A star. So maybe
Not similar to how SL2C has a parity or charge conjugation, which maps left to right. SL2's representations as operator.
well, probably it may be related because I always think that SL2C and this whole thing of sort of Unruh radiation is the same thing. But maybe I should write down the identity that Hawking derived, basically in deriving Hawking effect, is that if I have a left operator here and a right operator here, let's forget about A prime. This is just in space time and interspace. He showed that the vacuum state operates the following property. There's an e to the minus beta omega over 2, and then here you act with a dagger on the right. So this equation defines basically the Hawking vacuum, that if you annihilate, so the vacuum is not annihilated by the operators on the left, because this is exactly what gives rise to the Unruh effect. So if I annihilate a particle, which is actually lowering this by 1, it's the same as raising this by 1 and multiplying with the same factor. So this state actually satisfies that equation. So how do I now interpret this equation? So this equation is actually, well, maybe I should
I didn't say VAC is omega.
That is omega, that's right. It's the same state.
equation.
Yeah, I think actually, I think I want to start here, which I think is the same thing, but for the algebra, it doesn't matter. Normally, we think about as creation annihilation operators.
But in this particular case, it's
But
very
here you
simple.
see
S,
that
this is
J
the-
does two things. J multiplies it with this vector, and it changes what would have been, well, left into right. So this is why J is actually doing this thing of changing the left and the right. So it maps actually the
That's
ends
a
and the
parity
end.
operator in SL2C.
Probably
Or charge
that's,
conjugation.
that's charge point.
SL2R to SL2C is not SL2R times
So-
SL2R.
The nice thing is that by defining this operator, I define the property of the vacuum state that involves A and A prime, but by using only the algebra M. But I defined an operator S that does something quite non-trivial, namely it exchanges the algebra with its with
By
its
the way, this is SL2C analogy, says that there is another algebra, which is also following an algebra, where everything is fine. Because we include the charge conjugation operator as part of it, and from SL2R times SL2R, we construct SL2C. Here, the same thing.
So there's some way that this structure from type 3 to type 2 actually will involve adding this operator.
And then it's type 2?
Then it can become type 2.
Good.
So this is kind of the step that we're
Good,
going to do.
good. Let's finish today, maybe.